Good afternoon, everyone. So today's class, we are going to be doing a bunch of derivations for the permanent magnet synchronous motor. And next class, we'll try to get an intuitive feel for all the equations. We'll also do some demo next class as well. But today, we're just going to concentrate on deriving all the motor parameters for an permanent magnet synchronous motor. So before I do that, I have posted a link on Canvas for the last week module. Go to the link on Canvas titled Professor Ria's animation. He had created these wonderful animations that gives a very intuitive feel of what's actually going on in the motor. For instance, if you want to look at how the space vectors vary, or like say the H field and the air gap. So for the A phase, you can see clearly that it goes back and forth. B phase similarly phase shifted by 120 degrees, C phase shifted by 240. And when you sum them all up together, we have this rotating field that's there in the air gap. And the space vector notation that we use is basically tracking the purple line that's going all around. Right. So there are a whole bunch of animations that you have. Take a look at it. It kind of gives a very nice understanding of what happens in the motor. In addition, for all the animations that I used in the slides last week, I posted the code, MATLAB code for it. So you can change any parameters that you want in it and run it, and it will give you a new set of motors with new set of windings, whatever you want. And there is a section where you can enable the plotting of these phases as well in the code, so you can go ahead and enable that. All right, so in the homework, there is a question about once you have the space vector, I gave you the space vector values and asked you, I think the space vector value of the current or voltage, and I asked you for the phase currents at one particular time instant. Anybody want to tell me how you went about solving it? Has anybody done the homework? John?
Yeah, so like you get the same, they should all have the same magnitude, right? Which you get by dividing the magnitude of the space vector by 1.5. And then I did it by like using the cosine of the angle.
Okay.
And then they're like all phase shifted. But I think the formula that we have, it's like you put e to the j 0 and then e to the j 2 pi over 3.
Perfect. So once you have your space vector answer, so this is your ej0, ej 2 pi by 3, ej 4 pi by 3. And if you have some vector of some magnitude, some space vector magnitude is space vector magnitude is, and at some angle e pi j theta. To get the component of A phase current, that's basically just the projection of the space vector scaled by a value of 2 by 3. Right? And the projection is just 2 by 3 times is times also whatever the theta comes out to be. Right? And the 2 by 3 factor comes because if the space vector was say at angle theta equal to 0, then the projection is just along the same axis. Right? This is just 1. And we know that the space vector magnitude is 3 by 2 times the peak, 3 by 2 times any of the phase peak. Right? So to get the actual phase peak, you just multiply by 2 by 3 to cancel out that effect. Right? If you want to get the value around the B phase, project it onto B phase the same way. IB is same as 2 by 3 times the IS magnitude times cos of theta minus plus 2 pi by 3. Right? You're projecting it onto an axis, the 2 pi by 3 out. And then same for C phase, theta plus 4 pi by 3, that will give you the C phase projection. Is there any other way of doing it? Those of you who know matrix analysis. Any other way? So we did give a transformation from going to ABC to DQ, sorry, ABC to alpha beta or space vector. So if you have 3 currents, IA, IB, IC, the space vector transformation formula is just IA e power J2, IA e power J0 plus IB e power J2 pi by 3 plus IC e power J4 pi by 3. Right? This you can break it down into cos of 0, cos of 2 pi by 3, cos of 4 pi by 3, and then the imaginary component will be sine of 0, sine of 2 pi by 3, so on and so forth. So cos of 0, cos of 2 pi by 3, and then cos of 4 pi by 3, and then sine of 0, sine of 2 pi by 3, sine of 4 pi by 3. If you do this multiplication on the LHS, you'll get the real component of the space vector. So the space vector real part and the imaginary part. right? Because the sign components would be the J times the value of the space vector representation. Right, so if I give you these three, you can find out these two by substituting basically into this matrix, which is exactly what this is doing. This is exactly what the graphics is also doing here. But if I give you this, how will you get back this from the matrix? You can't invert that matrix, right? It's a rectangular matrix. But what else can I add to that matrix to be able to invert it? There's one piece of information that the matrix is not conveying, which is implicitly true whenever I use space vectors.
You put a 0 and then like a row of ones.
Perfect. So I put a 0 here, put a row of 1. These magnitudes can be anything as long as all the three magnitudes are same. What it's basically saying is that sum of the three currents, the value is always going to be 0. All right. Now I have a nice 3x3 invertible matrix. You can just plug this in MATLAB, take the inverse of it, put the real value of the space vector. Real value of the space vector is just going to be the space vector value, whatever the magnitude and the angle that I've given. So this is just going to be is magnitude cos of theta. This is just going to be is magnitude sine of theta. Okay. And the last element itself is 0. Take the inverse of this, multiply with this, and you'll get your IC. So however way you want to do it, it should end up giving you the same answer. Okay. Yep, sure.
Just so like I'm trying to understand what it represents like physically. So like when you're saying the space vector at that particular angle, does that represent like a moment in time or something?
Yep.
Okay.
So at any given instant of time, the currents are such that the space vector is at the position.
Okay.
Right? And what would happen is, so I think problem 3 you basically had to do where you plug in 3 sinusoidal currents and figure out how the space vector moves. You would have seen the space vector would be a fixed magnitude, but the angle would be e power j omega t plus pi by 2 or something, which basically says it's a space vector that's, so at time t equal to 0, the space vector would have been here. As time goes on, it's going to keep on rotating. At time t, omega t equal to 2 pi by 3, it would have reached here. And then later it will move here at 4 pi by 3 and then come back to here again. So in case of the H field and the B field and the air gap, it has a physical link to the peak of the H field, net H field. In case of the currents and the voltages, it's purely a mathematical conception that we have created, right? Any other questions? Right. So let's do some derivations today. And I would just pay attention to the class. I've posted detailed notes for the derivation that I'm going to be doing today on Canvas. Just pay attention in class. You don't even have to take notes. Just try to get an intuitive feel for what's going on because it's very critical. Otherwise, induction motor will become a very difficult topic to even begin to understand. Okay, so when we had a two-pole motor, our conductor density, distribution density, we gave a formula for, let's say, A phase was NT divided by 2 times sine of theta. Going forward, I'm not going to call this. So NT was number of turns, which in itself equal to NC divided by 2, where NC was number of conductors. So when we in our initial slide, when we saw the 50-turn motor that basically has 100 conductors, 50 conductors coming out of the page, 50 conductors going into the page. Whenever you get a negative sign here, that's just an indication that the conductors are going into the page. It says nothing about the current. All right, you can have a conductor going into the page. The current can still come out of the conductor. It just means that the conductor coming out of the page will have current going into it. That's all it means. All right, so the sign just means the way the conductor is wound, nothing to do about the current direction itself. Right, so going forward, what I'm going to be doing is replace this number of turns with NS instead of NT, because when we go to induction motor, there is going to be windings on the stator. We will look at the rotor as a set of windings as well. So we want to use NR for rotor, NS for stator. We're going to drop the T, but NS just means number of turns. So going forward, I'm just replacing NT with NS. That's all, right? Okay, so this is what the conductor density distribution was for a two-pole motor. And we indicated this in diagrammatically as just a coil. And we drew this coil such that the coil for an A phase, such that the coil is present at the point where the H field of the A phase or the B field of the A phase will be at its maximum. So this is called the A phase magnetic axis. So going back to our animation or Professor Riaz's animation, basically the H field due to the A phase winding was just increasing and going in the high positive here, and then going back to zero, negative, coming back to zero, increasing. So it was always along this x-axis. If you look at the B phase coil, B phase H field, that would have been along this axis. So this is the B phase magnetic axis. And then similarly, we had our C phase magnetic axis. And then the combined effect of this would have been a magnetic field that is rotating in space, completing a full rotation every single frequency cycle of the input frequency for a two-pole motor. Right. So now let's look at what would happen when we have a p-pole motor. Right. So for any p-poles, we want to figure out the conductor density distribution again, same way how we derive for a two-pole motor, we are going to do the same thing. So Na of theta, we do not know what the maximum conductor density is, so let's just put some random variable now and we'll figure it out what that comes out to. And then sine of P by 2 times theta. So what am I basically saying here? So if I had this, let's look at the case of a four-pole motor. And then the same thing repeats again. So previously, let's say, so there is 5 conductors here, 5, 5, 5, 5, 5, and 5. So we have a total of 20 conductors. And we have split it into portions of 5, 5, 5, and 5. In the previous case, for a two-pole motor, the way we split it was 10 on the top, 0 to 180, and then 10 on the bottom. So going from 0 to 180 on the top, and 180 to 360 on the bottom. So that's how we previously split it for a two-pole motor. We're going to retain the same number of conductors in a four-pole motor. And then we'll figure out what the conductor density is. We'll look at what the B field is, and then we'll see what can we do to increase the torque or increase the flux in the air gap later. For now, we're just going to assume in both cases, the total number of conductors is the same. Same total number of conductors in C. Okay. So let's try and figure out what would be the maximum, what is this end peak is going to be. So if I go around and integrate, let's say from 0 degree to pi by 2, right? So from 0 to pi by 2, Na of theta, that is going to be same as 0 to pi by 2, and some end peak times sine of P by 2 times theta d theta. So when I do, what I'm basically doing is I'm just looking at one set of pole and I'm integrating only the positive conductors for that particular pole. Right? So in a two-pole motor, we did this integration going from 0 to 180 degree. In a four-pole motor, we are doing this integration purely from 0 to pi by 2. In any p-pole motor, what would be the range of integration? If I want to figure out the total number of conductors within any one particular pole for a p-pole motor, what will be the range of integration? Would it always be 0 to pi by 2? What will be the value? Pi over t. Would it be pi over t?
Oh, yeah.
In a two-pole motor, what was it? 0 to pi, right? The range of integration. So pi over p would have given you pi by 2. So 2 by p times pi would be for any general p-pole motor. Right? So if you substitute for a four-pole motor, we are perfectly right because this is a four-pole case. Right? 1 pole, 2 pole, 3 pole, and 4 pole here. So if I put 4 there, I would get 0 to pi by 2, which is exactly the case. If I had a 6-pole motor, all of these windings would have been crammed between 0 to pi by 3 instead of pi by 2. That's all. And then you'll have another from pi by 3 to 120, 120 to 180, and then 180 to every 60 degree, you'll have additional set of poles created. Right? So if I do this integration, what should be the number on the right? So if I take the conductor distribution density and integrate it over one full pole, what will be the number on the right? Let's again start with the simple case of a two-pole motor. In case of a two-pole motor, what was the number on the right? if I integrate over one full angle from 0 to pi, what will be the total number of conductors over that integral? Anybody? Yep, Liam.
NC divided by.
NC divided by 2, perfect. So, because this was the case for a two-pole motor, right? Because if you go around and integrate all the windings, count all the windings in half of the motor, if you do from 0 to pi, that's basically half the motor. So the number of conductors should just be equal to n by 2. In our case, for a p-pole motor, so n by nc by 2 was same as our nt number of turns. Look at the definition on the right. And now we are replacing the definition for nt with ns, just so that we distinguish between stator and rotor turns. Right, so this is the number of, this would have been the case for a two-pole motor. For any p-pole motor, this is going to be 2 divided by p. So if you had two poles, there would have been just ns, which is the number of turns on the stator. If you had four-pole motor, it would be half of ns, right, which is exactly what we have here. So our number of conductors is 20. Our number of turns would have been 10. And this formula is telling me I should use 2 by p times 10. In our case, I have drawn a four-pole motor there. So 2 divided by 4 times 10. That would have been 5 conductors, and which is exactly what I have here, 5 conductors on this section. So if I do this integral from 0 to whatever, some other angle for any p-pole machine, that will be 2 by p times ns. And this integral itself, again, plug it into Mathematica, and they'll give you the answer. N is just a constant, comes out. The value comes out to 4 divided by p times. That's 4 divided by p. And then the RHS is 2 by p times ns. So our ns peak itself is just ns divided by 2. Somewhat counterintuitive. Irrespective of the number of poles you put on the motor, the winding density remains the same. Ns divided by 2 times sine of p by 2 times theta. It's not a function of p at all, right? But the number of conductors that come out of integrating over some particular range would be reduced though, because of this p by 2 factor within sine of within the sine term. So if I look at for a two-pole motor, so going back to a two-pole, this term would have been ns divided by 2 sine of theta, and for a four-pole motor, this term would have been ns divided by 2 sine of 2 theta, right? So in the top case, my conductor density distribution would have looked like this. In the second case, my conductor density distribution looks like this, right? But if I go around and integrate over the full range of one full cycle here, and do the integral over 1/4 of the cycle here, whatever value I get, that will be the double the value that I got for the four-pole machine. If I have the same number of ns turns here and ns turns here, right? Everybody clear? So this is the conductor density distribution for any p-pole machine. There is no additional poles on the conductor number itself. So today we are going to be trying to derive the inductance of the machine, and we are going to try to derive the torque of the machine. And there is one more term that needs to be derived, EMF, which I'll leave it as homework, which is basically just extension of whatever we do for torque and inductance. And the idea is because we want to create a motor model similar to the DC motor model that we have. We want to create an equivalent motor model, steady state equivalent motor model for a synchronous generator. Let me give you the model and explain what's going on. So the resistance part is pretty straightforward. You have 3 sets of windings, you pass some current. It is going to have some, you have some conductor wound on some core. It's going to have its own resistance. And since it's a bunch of coil wound on an iron core, it's going to have its own inductance. That inductance is what created all the magnetic field in the air gap that we analyzed. Right now, we were going to try and get an expression for the inductance so that we can put it in a circuit form, whatever we have as just magnetics, the magnetic field in the air gap. Right, and then finally, we so far haven't introduced the rotor yet. All we have done is analyze the stator part alone and the sinusoidally distributed winding of the stator. But the minute you put a rotor in, and the rotor starts to rotate, it is going to have its own magnetic field because the rotor is a magnet. And when the rotor rotates, it's going to have a magnetic field that's changing, which means the flux is changing. So there's going to be an EMF induced across the stator winding, which is experiencing this change in flux due to the rotating rotor magnet, right? And that EMF we are going to indicate it as ES. So our idea is today to calculate this value and calculate this value, and then the coupled mechanical system is going to create some torque, tau EM, and we are going to try and calculate this value, right? This in itself is pretty straightforward, right? If you take a copper wire and you're given a cross-sectional area and you know the conductivity, you can quite easily find the resistance based on the length of the wire that you use to wind the whole motor, right? And depending on the frequency you're using, account for some skin effect factor, and that's about it. So you can directly calculate the resistance value for a motor, pretty straightforward. So we're not going to waste time deriving it. Inductance gets a little bit tricky. The inductance that's causing the magnetic field in the air gap that interacts with the rotor. There is another term, leakage inductance, which we haven't introduced just yet. I'll do that once we have derived LM. Right, so this term we are going to derive, this term is going to be empirical. I'll explain what it is later, but we are not going to be doing a derivation for it. And then finally, we are going to be deriving the torque expression, and the EMF expression is same as the torque expression. So I'll leave it as homework for you to rederive it. It's derived in the notes as well, but it's straightforward. So these two are one and the same, similar to what you would get the relationship between the EMF and the torque in a DC motor. It was just KT times the current for the EMF or the torque, Ke times omega for the EMF, and Ke and KT were the same. We would end up showing that it's the same in this case as well. Okay. So let's start with the first one, the inductance. So let's say I didn't cover this in class today and I didn't post the notes, and I just asked you to, on your own, think about how to derive inductance of the stator winding. How will you go about doing it? We have already derived inductance in case of like a simple coil. What method did we use to derive? Or what all formulas do you know when it comes to inductance?
LDIDT.
LDIDT. Right? Is there any other formula? So in the past, when you derived the inductance for a coil on an iron core, we did use a different method as well. So we did use the LDIDT method and we used another method. So energy density method, right? So the energy in an inductor coil is half Li square. So today we'll do both methods and show both the results should come the same. So let's start out with a simple one using the energy density. So we have our rotor, we have our stator. There are a bunch of coils here. So let's so the B field in the air gap due to the A phase coil alone. Right, so we have A phase coil, we are pushing some current through it. So it's going to have a B field that's maximal along the A phase axis, and then something slightly lower as we go farther out. Again, all perpendicular to the iron at every single point, even though my drawing might not look like it at some points. With the peak along the 180-degree axis. Okay, so this is what the B field in the air gap is going to look like due to the current in the A phase winding alone. Can somebody tell me what the expression would be? What would the expression for the B field in the air gap due to A phase winding alone? For some current type. You don't even have to look at your notes for this. Just think about how you figure out the B. Yep.
Is it Ni over mu times sin of theta?
N times I sine of theta. It wouldn't be divided by mu. Mu would come here. Right? So how will we do that? Because we have a bunch of conductors. You take a loop. Right? Take the biggest loop that encloses all the positive set of conductors. So For instance, let's say we are doing it for this 4-pole motor. So we would have taken this tiny loop, it would have given us integral h dot dl equal to some Ni. We know the N here, and then we know the current is just I for all of them. And then we'll take another loop, and then another loop until we get all the loops within the coil, and that will be the point where the H field is maximum. So for this case, this would have been integral H dot dl is equal to this total number of conductors in the loop that we have chosen, which is 2 by P times Ns. Right? So for the loop that I've drawn there, it's going to be 2 by P times Ns times current in each of them must be equal to integral H dot dl. There are two air gaps, one crossing from here to here, another crossing from here to here. So we have Lg and then Lg. So we have 2 Lg. So H is going to be equal to Ns divided by P times pi divided by Lg. Right? This two just cancels out. So this is going to be the Hg at this point along zero axis. As we go around other angles, it is going to go from zero, peak value to zero, and then go negative, and then go to the negative peak where it's coming back into the rotor from the stator. So our expression is going to be N divided Ns divided by P. For any p-pole motor, in class we did for a 2-pole motor, which gave us Ns divided by 2 times sine of P by 2 times theta. Right? So this is what it's going to be divided by Lg. And this mu naught factor comes because what I have on the right there, that's H. And the H is related to the B just by just a mu naught factor, because we're only interested in the B field in the air gap. Right? Yep, you know.
Do we always count the 2 air gaps, like as you go out and come back in?
Yep. Okay. Yeah, so it depends on the path, however you choose the path. So the way I've chosen the path, we have 2 air gaps, but you can choose a quite an odd pathway that goes through the air gap multiple times. There is no restriction on what the loop needs to be. So you can choose a loop like that looks like this. Right? So every time you cross the air gap, it will be an integral H dot dl. Each of that would contribute to an Lg. But the problem is if I choose a loop like this, I don't know what this H is here, and here. I have a single equation, but 1, 2, 3, 4, 5, 6 H that I need to calculate, which I can't. But if I choose the symmetric loop, I know the H here. So I can, because these, at least I know that they have to be the same. So I can pull that out common, and then there's one Lg. But yeah, depending on how many times you cross the Lg, that Lg would multiply with your H term, right? It doesn't have to be just twice. It depends on how many times you cross. Any questions? Okay. So this is going to be our B in the air gap at any given angle theta. So at any given angle theta, this is what the B is going to be in the air gap due to current in the A phase winding alone. Okay. So anybody remember the formula for the energy density? Because what I need to do is here I have the expression for energy. Right? I have the expression for energy as half Li squared. If I can somehow figure out what the energy in this air gap is due to current flowing in this coil, then I'll get an half Li squared. Then I'll get an expression on the right. Then I can cancel out the I squared terms on the expression that comes on the right, and this one, and whatever I left with will give me the inductance. That's the idea. So for this, what we need to do though is this current has caused some B field to emanate in this air gap, and anytime there's a magnetic field, it has an associated energy with it, and we need to figure out what that energy is in that field, right? So that's the idea. So first we start off with energy density, which is just 1 by 2 mu naught times B square. Again, this we had derived. So that's our energy density. And once I have the energy density, I can figure out what the energy is going to be. So let me take a tiny cross-sectional area in the air gap. So let's say I consider this a cross-sectional area, this length Lg, and the motor itself has some vertical length. Let this length be some capital L. And the rotor radius, let's consider to be R. and it's some angle. So let me redraw it here. Okay, so we are considering a tiny section, an incremental section in the air gap, which is at some angle theta from our A phase axis, and the incremental wall angle itself is d theta, and the rotor radius is r. The length of the air gap is quite tiny compared to the length of the rotor, so we are not going to worry about the mean length or anything like that, just to keep our math simple. Right, so this is the tiny section that I have, and the incremental volume for this section is just going to be, this length is r d theta, r d theta times the vertical length times the thickness, which is Lg. So this is the incremental volume that I have. What is going to be the energy of the magnetic field within the tiny volume that I've chosen? How do I figure out the energy of the magnetic field within that volume? Anybody?
Multiplied by the energy density.
Perfect. So we only have the expression for energy density. Mu density is just 1 by 2 mu naught b square. And the answer Trisha gave, basically to figure out the energy in the incremental volume, take the energy density that we have and multiply by the incremental volume that we have. Okay? This is the density, that is the energy per unit volume. Multiply by the incremental volume, you have the energy in the incremental volume. So let's plug in all the values. 1 by 2 mu naught, my B of theta itself was equal to mu naught ns divided by 2. So ns divided by p times I divided by Lg times cos of p by 2, not sine. It should be cos, because the B field is maximum at an angle theta equal to 0, and B field is minimum in a two-pole case at angle equal to pi by 2, in four-pole case at angle equal to pi by 4. So this is our B of theta. Instead of writing ns divided by p every time, I'm going to introduce a new term, nsp, which is the number of turns per pole, per phase. Right? So just so that I don't have to do ns divided by p every single time. So let's substitute for b square, whatever expression that I have on the top there. So I have mu naught square minus p square I square divided by Lg square times cos square p by 2 theta times my dV, which is r d theta times L times Lg. Lg square gets cancelled. Mu naught square gets cancelled. So what we are left with is 1 by 2 mu naught times RL divided by Lg times I square. Let me add a subscript, basically the current in the A phase, times cos square p by 2 times theta times the d theta. Right, so this is the energy in the tiny incremental volume that I have chosen due to current going in the A phase coil, and which establishes its own magnetic field, and the magnetic field has some energy, and we computed the energy in this tiny volume. Now we want to figure out what the total energy is across the full pole phase. Right? So we are going to figure out what the total energy is. Q2 equal to 0. I'll let you decide what the upper limit of this integral is going to be. Right, so I want to figure out what the energy is. Let's say in case of a two-pole motor, the integral is very obvious. I'll do from 0 to the full angle, right? From 0 to the full coil, 0 to 2 pi. If I want to do for a p-pole motor, what would be my angle upper limit of integration? Because I just want to figure out what the energy is due to a set of coils. So if I have this set of conductors coming out of the page and this set of conductor going into the page, their combined effect sets up magnetic field in the air gap, which goes in on the side, comes out of the side. And then the other set of coil does the same thing, but for this set of magnetic field on the side. Right? So all I'm interested is then what each of those coil created, what energy they contributed to. Right? What would be the, Lily?
Pi by P.
Pi by P. So pi divided by P. So let me write it as 2 by P times 2 pi. Sorry. Yeah, that's right. So 2 by P times 2 pi. Because when we had a one phase, just a one pole, two pole case, our whole area of integration would have been from 0 all the way to 2 pi. Right? Because there would have been a bunch of positive conductors on the top, negative conductors on the bottom. The combined coil created the magnetic field, which created some energy. The total energy would be integrating over the full air gap. Right? If I had a four-pole motor, just the half section is what I need to integrate because the other half energy is contributed by the other two coil combinations. Yep, Jonah.
So that model we had before, is that representing the entire motor? Is it just like one set of poles?
Which model?
Like the circuit model that you drew before?
No, that's for the full motor.
Okay.
Yeah, so whatever I'm deriving is the energy of this half, let's say in a four-pole case, this half alone. But then what happens with the inductance will depend on how I connect this winding with this winding, right? There are multiple ways of connecting them, right? For now, just hang on. We are deriving just the energy of one set of coils alone, and then we'll see how it interacts with the other set of coils. But the circuit diagram that I drew is an equivalent circuit for the full motor, or it's a per phase equivalent motor model, right? So once we plug in these values, so 0 to 2 pi, 2 by P times 2 pi, and then all the other terms on the right are constants. Mu naught RL divided by LG times IA. Leave anything out? That's about it. Cos square P by 2 times theta, d theta. Again, don't stress too much if you're not able to keep full track of the equation derivation. It's quite a bit involved, but I've posted detailed notes for it. Just pay attention in class. So this integration comes out to pi. Again, plug it in Mathematica. Pi times 2 by P. Plug it in Mathematica and give the answer for you. So the final expression is 1 by 2 mu naught pi RL divided by LG NSP square by A times 2 by P. It should be a I square, I square. Right, so this is what we would end up getting as our energy in the air gap due to just a single set of coils of one particular phase for one particular pole pair. Right? Everybody clear? This part? Okay. How will I get the inductance now? How do I get the inductance? Simply.
1/2 L I squared.
Perfect. So this is equal to, this is the reason we started off the whole adventure. Half L I square cancels, half and half cancels. So my inductance is just so my inductance of one phase due to a pole pair is equal to mu naught pi RL divided by LG times NSP square times 2 by P. So this form should remind you back to the inductance we got for a solenoid, which was basically mu naught times n squared, mu naught n squared A divided by L. Right? The L was basically the length of the core. If you put a tiny air gap, that's what determines the whole magnetic field in essence. And then the area was basically the cross-sectional area of the core. In some sense, this is the equivalent cross-sectional area that we get for the sinusoidally distributed winding. So the expression is very similar. So it's mu naught n square, some equivalent cross-sectional area divided by the length of the air gap. And then there is this additional factor of 2 by p that comes into picture. So what happens is, going back to Jonah's question, whether the inductance that I derived is same as the inductance in the equivalent circuit that I wrote, it is not. Because when I have a two-pole motor, this inductance would be same as the inductance that I had in the equivalent circuit. In case of a four-pole motor, I have multiple choices. So I wind let's say I wind this set of coils and this set of coils, right? So I will have one winding and then one winding coming out. And then I can do the same for this one as well. One winding here and then one winding coming out. So I have two set of separate coils now. I have multiple options. I can connect these in series, right? And then have these two windings come out, or I can put them in parallel and have two set of windings come out, right? And this is the case when you have just 4 poles. When you have 6 poles, you have multiple options. You can have coils of 2 to 2, parallel them up to two coils in series and then 3 sets in parallel. Or you could have 3 coils in series, 2 sets in parallel, or you can have all of them in parallel, all of them in series. And you go to more and more pole counts, it becomes more and more options that you have how you parallel them and combine them. If I were to tie all of these windings in series, what will be my net inductance? So that is the inductance for a single phase for just one pole pair. And then similarly, I will have an inductance for another pole pair. If both of these coils were connected up in series, like the case here. So one coil pair is connected in series with the other and I take the coils out. What will be the net inductance?
2L.
Perfect, just 2 times. So if I do it in series connect all pole pair coils, then my L net is just going to be, in case of 4-pole motor, it would have been 2 times. For any general p-pole motor, it would have been p by 2 times L of this one, L1 pole pair, right? So which in effect would just be equal to mu naught pi RL divided by LG times NSP squared, if I connect them in series. So in the textbook, Professor Mohan, the derivation he has done is for the case where all the pole pairs are connected in series. Right, all the coils creating the poles are connected in series and you have these windings coming out. So that's why the expression in the textbook would just be this form alone without the 2 by p factor. But again, there are multiple ways you can connect them. If you were to connect them in parallel, then your inductance would just be divided by a factor of p by 2. Yep, divided by a factor of p by 2. So you end up with net inductance being this 1 times 2 by p the whole square if you connect these windings in parallel. When would you connect in parallel? When would you connect in series? When you design a motor? We already saw this when we did the DC motor armature winding. We said that lap winding we use in case of certain type of motors, wave winding we'll use in different kind of motors. When would you decide to connect these coils up in series? When would you decide to connect them up in parallel? What would happen to the current if you connect them up in parallel?
You need twice as much.
You need twice as much. Obviously, the other way of stating the same thing is if you connect these coils up in parallel, you're basically splitting the current. Right? So if you have a motor that you need to design for a very large current, then you cannot pass a very large current through all of these coils. Your core would saturate typically out. So what you do is you split them up in parallel and then pass currents through them so that if it's 100 ampere split across 10 poles, you would just have 10 amperes in each of those coils. So much more manageable. Then when would you connect them up in series? So if you want to split the current up because the current is too large to handle, you would wind them as in parallel. When would you connect them up in series? Yeah, Chris.
Is that if you like wanted more torque?
You can create more torque in either of those arrangements.
Well, I guess it would just be more current.
Would you repeat it?
Wanted more current through.
If you wanted to put more current, you would have to split them in parallel.
Oh, okay.
Right? Because if you split them in parallel, basically the inductance is much lower. So when you put a voltage across, the current can be quite large. Right? And the large current can split across multiple coils and then create whatever torque or whatever you need. So if you want a motor that needs to take a lot of currents, then you would put the windings in parallel so that the current can split across multiple coils and then you have manageable currents across each of those coils. What would be the complementary pair of it? Yeah, okay.
On a small current, but you still want to use all the coils.
All right, when would you want to have a small current? What is the alternative to it? When you want to have a large voltage, right? When your motor is connected to a very large voltage source, then you would connect the inductance up in series, so that the voltage splits across multiple coils to a manageable level, so that there is no high voltage across any of those single individual coil. All right, so when you have very large voltage that you need to handle, you will put it in series. When you have very large current that you need to handle in your motor, you will put it in parallel. Right? And the way you'll get very large voltage could either come from your grid side, or you have designed an inverter that is pushing the voltage to a very large level so that the inverter current is very small so that you have very low conduction losses. So it's a multiple decision factor that will decide whether you want a motor to have in parallel and have high currents, or put it in series and operate at a very large voltage, right? And depending on the speed as well, that factors will be determined. Right? Any questions so far? So now let's derive the inductance using the second method. So instead of doing it for a generic 3-pole case, let's keep it simple. Let's do for a 2-pole case. So let's start off with, so our expression is E is L di by dt. Again, when we derived this expression, we made a note saying that the L can be brought out only if the inductance is in varying. In reality, that was actually d by dt times Li. And we said that when we go to induction motor, a permanent magnet synchronous motor, the L still doesn't vary. But once we go to an induction motor, the L starts to vary. That way, we can't put the L out in case of an induction motor. But at least in a permanent magnet synchronous motor, it's absolutely fine to take the L out, right? So this is also equal to, from Faraday's law, n d phi by dt. And we are going to take this n term inside. That in itself is not varying, so you can take it inside. And this we are going to introduce a new term. In the textbook, this term has already been introduced in chapter 2 or chapter 3, but I wanted to hold off for a while. Flux linkage, lambda. So basically, if you have a bunch of coils, if you have one coil and you have some flux passing through it, you're going to get some voltage, E. And if you have two set of coils, then the voltage is going to be another E for a total of 2E. Right? So basically, it's just not the flux alone that matters, but number of flux linking how many number of coils that you have. Right? So we are going to introduce a new term for it, lambda, which is equal to n times phi. So going back to our expression there, is equal to d lambda by dt, which implies lambda, our flux linkage is just L times I. Again, this is just a new term we are introducing, nothing particular about it. So we have our expression for EMF. If we can figure out what the flux linking a coil is, then we can equate whatever the d lambda by dt to this L di by dt, and then we can get a nice expression for our inductance. So let's try and do that. So let's say we have again our stator. And we have some coils here. And some coil here. And then we have the air gap. So if I want to find out the inductance of same thing, whatever is on the top is just repeat from the bottom. Right, so what we are trying to do is basically figure out what the flux through this particular coil that I've drawn here is. Right? Let's say it's at some angle theta. And we want to figure out what the flux through this loop that I have drawn here. So if I know what the flux through this loop is, so this is basically one conductor going in, coming out, going in, coming out, going in, coming out, right? So we have three set of coils, three set of conductors, six set of conductors that forming a three loops. And if we can figure out what the flux through the coil is, then we have a nice relationship that lambda, which is n phi, is equal to Li. If we can figure out this phi, then we can equate this term and get our inductance term. Same as how we did for our energy equation. We had some energy expression on the left that we equated to half Li squared, cancelled out the I squared terms. Whatever we left with was the inductance and we got it. So we're going to do the same thing for this case. How do I figure out the flux through this coil? So any set of coil at some random angle theta through this whole loop, how do I figure out what the flux through it is? Any guesses? It's a bit of a complicated problem to solve. What formula do you know for flux?
Is it F over reluctance?
Will you repeat it?
F over R?
F over reluctance, but then it's compounding the problem even further, right? We don't know what the reluctance is for this motor. At least not yet. What is the formula?
B field times area.
B field times the cross-sectional area. So our flux is just integral B dot ds. So this is a cross-sectional area for this loop, which is pretty straightforward to figure out, right? So let's say, so this whole thing goes all the way down, right, to the full length of the motor, and there is some B field coming on this side and then B field leaving out of it. So this cross-sectional area itself is pretty straightforward because this is the rotor radius, this is the length of the motor L. Right? So 2 times the rotor radius times the length will give you the cross-sectional area. How about the B? Do I know the B through the loop that I've drawn? Thomas, you're saying yes?
It's like Ni over something, right? I don't remember.
But does that turn across the iron core cross-section? We know the B in the air gap, we do not know what the B in the iron core is. Right? We never derived an expression for B in the iron core just yet. Because in fact, the B in the iron core is a very complicated picture because you would have some rotor shaft here, you might have some cooling ventilation holes here, right? And the B field, the actual picture and the B field way it would look like would be quite complicated picture. In the iron core, how it will come out on the rotor side. So analytically, we do not know, we do not have an expression for what the B in this section of the rotor's iron core is, right? But how do we, there is still a way of figuring it out though. We don't know what the B field is, but we can certainly figure out what the flux going through the surface area is. So let's start off with where do we know the flux? Where do we know the B field in this motor? What have we calculated the B field for, for this motor?
The air gap?
In the air gap. So we know the B field over this full section. At every single point, we know the exact B field, and we have an expression for it as well. BA of theta is mu naught NSP times I divided by LG times cos of theta. Right? So we do have a nice expression for, so alpha for now. I don't want to use the same symbol theta. Right? So for every single point in this air gap, any given theta, I know exactly what the B field is. But what I'm interested in is not the B field here, but actually the flux crossing this loop that I've chosen here. What can I do? Yep, John.
Did you find the total flux like on like 1/2 of the air gap, like where the line is dividing it?
Perfect. So if I figure out what the flux crossing here on this surface is, that must be the same as the flux leaving out of this surface, right? Because it's a closed surface. What I've chosen there, if I take this half, and this is basically the air gap. So I know the B field at every single point in the air gap, and that's the formula that I have there. And I can integrate the B field over the surface area and they'll give you the flux entering this surface area. And that flux must be exactly same as whatever the flux is leaving out of the surface area. However, the shape of it leaves and doesn't matter. Right? So the total flux that's leaving here, let's call this the surface 1, must be the same as the total flux entering this side. Flux of surface 2. Right? So far, clear? So what I'm basically saying is if you go around a closed surface and integrate B dot ds, Gauss's theorem for magnetics, the surface integral must be equal to 0. So I can split it into two surfaces. For surface 1, I can do B dot ds, and then I can do the same integral for surface 2, B dot ds. That sum must be 0, because whatever came in must be the same as whatever leaves out. So what I'm interested in is actually the flux leaving out of this surface, right? So I'm interested in this surface integral of surface 1. So this flux of the loop. So the flux of the loop is same as, so that's basically this term, flux of the loop. So pi in the loop is just equal to negative integral surface integral over the surface 2 B dot ds. Right? So going back to that section that I had there. So this is my lab here. And basically we are going to integrate B at every single point, starting with some angle theta, going all the way to theta plus pi. Right? So if I integrate all of the flux coming in, then that will be the same as the flux going out of the surface. So I use theta or not? So let's do that integral. So let's start off with, again, same a tiny cross-sectional area. Let me choose this tiny cross-sectional area. Right? And let the radius be r, and let the angle of this cross-sectional area be d theta, and with some angle theta. So I know the B field here, the cross-sectional area ds is just going to be equal to r d theta times L, right? The total length of this rotor. And my incremental flux in the tiny surface I have chosen is going to be my B at angle theta, which was mu naught times NSP times I divided by LG times cos of theta times this. So this is my B at any given angle theta. So at any given angle theta, this is what my B is going to be, okay, which is what I've drawn here. B at some angle theta. And if I multiply that B over some tiny incremental cross-sectional area, which is R d theta would be this, and then the length L would be this. So the surface area of the incremental section that I've drawn would be R d theta times L. If I multiply that, I'll get the flux through the tiny section. So I have R d theta times L. Now we are interested in figuring out the total flux. So the total flux phi through that single loop that I've chosen, through the loop at some angle alpha is going to be equal to integrated over the period alpha to alpha plus phi with a negative sign, because the flux entering, leaving the other side is the same as the flux entering this side. So we have the negative sign coming from that expression there, times this d phi. So it should be equal to negative alpha to alpha plus pi. Everything else is a constant. The only term is cos theta d theta and the integral theta d theta. The rest of the term is just mu naught NSP R times L divided by LG times I. So R times L, NSP, LG, mu naught times I. Right, everything covered. So if I do the integral on the top, pretty straightforward to see. You would end up with cos of alpha negative outside, cos of alpha plus pi minus cos of alpha. So you would end up with negative 2 sine of alpha. So when you integrate cos, you'll get sine. Negative was negative times mu naught NSP RL LG times I. So the same as 2 mu naught NSP RL divided by LG times I times sine of alpha. How do I get the inductance? Is my derivation done? How do I get the inductance? Lily.
Multiply by n divide by I.
Multiply by n.
If you say that your flux linkage is equal to Li,
Perfect.
just divide.
So my flux linkage, so this is just the flux. So this is the flux of loop at coil alpha. If I multiply by this by n, that must be equal to Li. Is it true though? Because at the end of the day, this expression that I have here must match with this expression. But I am left with a sine alpha term in my equation. Or the derivation is still not complete. What am I missing? I only derived the flux through a single loop. Right? There is a whole bunch of other windings that are part of the A phase. I haven't completed the full integration just yet. I only found out what the flux through this coil is. Now, if this flux varies, there is going to be developed across this 3 coil, this 3 coil. But then there are other coils here. This coil is here, this loop is here, this loop is here. So there are a whole bunch of other loops that are yet to be figured out what the flux through them is. And the variation in the flux is going to create its own EMF. And if these coils are all connected in series, which they are for a 2-pole motor, then you would end up with some of all of those adding up together. Right? So it's not just this one loop alone. There is still a bit more to do for the derivation. So let's go ahead. So what we have is the flux linkage of phi of loop at alpha. But what we need to now do is figure out the same for all of the coils. Right? So for coil at some other angle, for coil at another angle, so on and so forth. So what is my n going to be? How do I figure out what the n is for this coil? Let's say for some angle d theta. How do I figure out the number of coils in that angle? For a tiny span d theta, how will I figure out what the number of coils in that angle is? How did you figure out the number of conductors that needs to go into each slot of the stator? What did we do there?
NS over 2 sine theta.
What did we do?
NS over 2 sine theta.
NS over 2 sine theta, or basically NS over 2 times sine theta. Is this the number of conductors in the slot though? What is this though? Is this the number of conductors or is the conductor density distribution? This is the conductor density. So NS of theta, this is the conductor, the conductor, number of conductors that needs to be at every single radian, right? Number of conductors per radian. So this is what we introduced as an ideal way we want to wind our motors, continuous distribution of sinusoidal set of conductors, which is not practical. So we said for a motor with finite number of slots, what do we do to this function to get the actual number of conductors we need to put in each of those slots? So this is the conductor density, number of conductors per radian. If I want to figure out the number of conductors that needs to be in some particular angle, then I just need to integrate it. So if you remember for the 6-slot motor, 12-slot motor, we did this integral from 0 to pi by 3, 0 to 30 degrees, sorry, 0 to pi by 6, ns of theta, and we got this value to be 3. And then we did the integral for pi by 3 to pi by 6, pi by 6 to pi by 3, ns of theta, and we got our value, I think, 9 or something. And then we did for the other range, we got, I think, 12. Right? That's how we got 6, 18, 24 for a total of 50 turns in the motor. Right? So basically, for any given range, integrate over the range this density function, and that will give you the number of conductors that needs to be in the slot. So if I were to give you the range as some incremental angle d theta, how do you figure out the total number of angles in the total number of conductors in that angle? How many of you are still not clear about this? If you're not clear, let me know. It's quite an important concept. Everybody clear on this part? Okay. So this is the conductor density. And if I give you the conductor density to figure out the number of conductors, you basically integrate over the range that you want to figure it out. How would I figure out the number of conductors in this range angle d theta? So this is my density, the number of conductors. This is going to be ns of theta times d theta, right, for a tiny incremental angle. So we have flux at any particular loop is this, or flux linkage at some angle alpha is just going to be equal to the number of conductors at that angle times flux of the loop at alpha, and this itself is basically the equation that we have there. Ns divided by 2 times sine of theta times d theta times flux at the loop that I have from the expression before. Right? Mu naught 2 times mu naught NSP RL divided by LG times I times sine of alpha. So any particular angle alpha. Then my angle alpha, this would be d alpha, and we want to figure out the total number of conductors in that particular angle. Right? Once we have the flux linkage of that particular loop, how do I figure out the total flux linking all the coils? So let's go through the process. So what we started off with. So we have our equation L times Li must be equal to lambda, which in turn is equal to n phi. Right? So what's the second step that we did? We started off with some conductor. Just took a bunch of conductors at some arbitrary angle alpha. Right? And then we figure out what the flux through this is going to be. So what we have in our step there is the flux through the loop of conductors at some angle alpha. Right? So we took another side, figured out the B field at every single point on this semicircle, and we integrated over the surface, and we said that must be equal to the negative of whatever the flux is leaving out of the surface. Right? So that's what we did at second step. At the third step, what we did is now we have the flux cutting through this coil. We want to figure out what the flux linkage would be cutting through this particular set of coils. So flux linkage through the set of coils at loop at angle alpha is just going to be equal to whatever the number of conductors are here, right, over this spread. Let's call it some angle d alpha. So whatever the number of conductors are at angle spread d alpha times the flux through the loop at the angle alpha. So if I had one conductor here, then there would have just been 1 times the flux at that loop, the flux crossing through this loop. If I have two conductors, that's just going to be 2 times the flux. That's going to be the total flux linkage because the flux is linking two of those coils. But the number of conductors that I have is given by my conductor density function, which is Ns divided by 2 times sine of alpha. Right? That is the density. If I want to figure out the number of conductors, I'm basically going to integrate it. But to have if it was a finite number of slots, I would just integrate it. But now I'm doing it for a generic motor where there are any number of slots. So I'm just going to set it up as some angle alpha, d alpha, an incremental angle. And if I multiply my density function, ns of theta, by that angle d alpha, I would basically get the total number of conductors in that suite. Right? If I multiply the total number of conductors by this flux at the loop at alpha, then I would get the flux linkage for this particular loop alone. Now, have I completed it or yep counts?
This, I want to double check my understanding. This isn't the inductance of like the phases. This would be the inductance of the motor as a whole.
We are only doing it for one single phase right now, right? We are only looking at just the A phase alone.
Okay.
Right? I haven't considered, if we were to do all the other phases, then these currents that would come into the picture would also change.
Okay.
When I put Li equal to some N5, that is one particular I. Now we'll repeat the same thing for B phase because again, when I use this Ns divided by 2 times sine of alpha, this is the density function of A phase alone.
Okay.
Density function of B phase would be sine of alpha plus 2 pi by 3. Density function of C phase would be alpha plus 4 pi by 3. Right? So I have not even considered other two phases just yet. So it's only for a single phase. Right? So what will be my next step? Yep.
Would you integrate this thing from alpha to like 0 to 180?
Perfect. So next step that we need to do. So I have basically the flux through one single coil alone, one set of coils at some particular angle, but I need to know the total flux linking all the set of coils for a phase motor. Right? So what I need to do is to figure out the total flux linkage of A phase. Up to here, I just have a single set of loop of A phase at some angle alpha. Get the total flux, go from 0, integrate it all the way to pi, whatever I have here. Right? So we have lambda at loop 2, which is equal to ns of theta times d alpha times pi of loop at alpha. So let's plug in those values. So let's see, what do we have? Pi at loop alpha is going to be 2 mu naught NSP RL divided by LG times I times sine of alpha. And then my density distribution itself is Ns divided by 2 times sine of alpha. Right? Instead of doing Ns divided by 2, I'm just going to call that NSP. We are only considering 2-pole motor, so Ns divided by 2 is NSP. Sine of alpha times R d alpha 2. Right? So integrate this all the way from 0 to pi. That is going to give you your total flux linking A phase. So once we do this integral, you would end up with mu naught NSP RL divided by LG. NSP becomes NSP square times I times integral 0 to pi sine square alpha d alpha with a 2 outside. This integral will give you pi by 2. You end up with mu naught NSP square mu naught pi NSP square RL divided by LG times I in the A phase current. Now this must be equal to L times I cancels. So it end up with mu naught n pi times NSP square R by LG. Exactly the same expression that we have here. Here we derive for a general p-pole motor. If a 2-pole motor, 2 divided by 2 cancels. So you just end up with mu naught pi RL NSP square divided by alpha divided by LG. Alright, exactly the same expression that we have here. Very clear? Any questions? Just a second here. So this is a bit of a quite complicated derivation, but go back and take the look at the notes because we will extend the same derivation when you go to synchronous induction motor And we'll extend the same derivation next class when we want to find out the flux linking from B phase winding into A phase. So before coming to next class, go and take a look at this derivation. Again, I've already posted the detailed derivation for everything we're going to do today and Friday. So please take the time to take a look at the derivation.